Space is amazing and mysterious. For hundreds of years, people have looked up at the stars and wondered what is out there. Because space is so far away and hard to study, many wrong ideas have spread about it. Some of these myths come from old science that we now know is not correct. Other myths come from movies and television shows that make space look different from how it really is. Some myths are just misunderstandings that get passed from person to person. In this guide, we will look at many common myths about space and explain why they are wrong. We will use simple words and real science to help you understand the truth about our universe. By the end, you will know the facts about space and be able to spot false information when you hear it. Myth 1. There is no gravity in space. One of the most common myths about space is that there is no gravity up there. Many people think that astronauts float in space because gravity just stops working once you leave Earth. They imagine that gravity only exists on planets, and that space is a place with zero gravity. This myth is completely wrong. Gravity exists everywhere in space. In fact, gravity never stops working. It gets weaker the farther you are from an object, but it never goes away completely. Gravity is a force that pulls things together. Everything that has mass creates gravity. The Earth has gravity. The moon has gravity. The sun has gravity. Even you have gravity, though it is very tiny because you have much less mass than a planet. So why do astronauts float in the space station? They are not floating because there is no gravity. They are floating because they are in free fall. This means they are constantly falling toward Earth, but they are also moving sideways so fast that they keep missing the Earth. Imagine throwing a ball. The ball goes forward, but it also falls down because of gravity. If you could throw the ball fast enough, it would fall toward the Earth, but never hit the ground because the Earth curves away beneath it. This is what the space station does. It is falling toward Earth all the time, but it is moving so fast sideways that it keeps missing the Earth and going around it instead. The astronauts inside the space station are also falling at the same speed as the station, because everything is falling together at the same rate. It feels like floating. Scientists call this being in orbit. Gravity is what keeps all the planets moving around the sun. The sun is huge and has very strong gravity. This gravity pulls on all the planets and keeps them in their paths. Without the sun's gravity, all the planets would fly off into deep space in straight lines. The moon orbits around Earth because of Earth's gravity. All the moons in our solar system orbit their planets because of gravity. Gravity is also what makes stars form from clouds of gas and dust. It is what holds galaxies together. Gravity is working everywhere in the universe all the time. The International Space Station orbits about 400 kilometers above Earth. At that height, Earth's gravity is only about 10% weaker than it is on the ground. If you could stand on an invisible platform at that height, you would weigh about 90% of what you weigh on Earth's surface. So the astronauts are not in a place with no gravity. They are in a place where gravity is almost as strong as it is on the ground. They float because they are in free fall, not because gravity is missing. Myth 2. The sun is on fire. Many people think the sun is a giant ball of fire burning in space. They imagine flames shooting out from its surface like a massive campfire. This seems to make sense because the sun is hot and bright, and fire is hot and bright too. The sun is not on fire. There are no flames on the sun. Fire is a chemical reaction that happens when something like wood or gas combines with oxygen and releases heat and light. Fire needs oxygen to burn, and there is no oxygen in space. The sun could not be on fire even if it wanted to be. Instead of burning, the sun creates heat and light through a process called nuclear fusion. This is very different from fire. Nuclear fusion happens when the centers of atoms join together to make new atoms. This process releases enormous amounts of energy. In the center of the sun, the temperature is about 15 million degrees Celsius. That is 15,000,000 degrees. At these incredibly hot temperatures and under crushing pressure, hydrogen atoms smash together and combine to make helium atoms. When this happens, a tiny bit of mass gets converted into energy. This energy travels out from the sun's core and eventually reaches us as light and heat. The amount of energy the sun produces is hard to imagine. Every second, the sun converts about 600 million tons of hydrogen into helium. That is 600,000,000,000 tons every single second. The tiny amount of mass that gets lost in this process becomes energy, according to Albert Einstein's famous equation. In simple terms, Einstein discovered that mass and energy are related. A tiny bit of mass can become a huge amount of energy. This is what powers the sun and all stars. The sun has been doing this for about 4.5 billion years. That is 4,500,000,000 years. It has enough hydrogen fuel to keep going for about another 5 billion years before it runs out. When people see pictures of the sun with bright areas that look like flames, they are actually seeing hot gas moving around on the sun's surface. These are not flames from fire. They are flows of superhot plasma being pushed around by the sun's powerful magnetic fields. Myth 3. Space is completely empty when people look up at the night sky and see the vast darkness between stars. Many think that space is completely empty. They imagine it as total nothingness, with only planets and stars here and there. Space is not empty at all. While it is true that space is much less crowded than Earth, there is actually stuff everywhere. Between the stars, there are clouds of gas and dust. Most of this is hydrogen, the simplest and most common element in the universe. There is also helium and tiny amounts of other elements. These clouds can be enormous, stretching for many light years across space. In some places, these clouds are thick enough to block light from stars behind them. We can see these as dark patches in the sky when we look through telescopes. In other places, the clouds glow because nearby stars light them up. New stars are born from these clouds. Gravity slowly pulls the gas and dust together over millions of years until it gets dense enough and hot enough for nuclear fusion to start. Then a new star lights up. Space is also filled with cosmic rays. These are tiny particles, mostly protons, traveling through space at incredibly high speeds. They come from exploding stars and other violent events in the universe. These particles zoom through space and hit everything in their path, including Earth. Luckily, Earth's atmosphere and magnetic field protect us from most of them. Space is full of light and other forms of radiation. Light from stars travels through space in all directions. There is also invisible light that our eyes cannot see, like infrared light, ultraviolet light, X-rays, and radio waves. All of these are forms of electromagnetic radiation, and they fill space. The universe is also filled with something called the cosmic microwave background radiation. This is very faint radiation left over from the Big Bang when the universe began. It is everywhere in space, though it is very weak and cold now. Scientists have discovered that most of the matter in the universe is invisible. We call it dark matter because it does not give off light or any other radiation we can detect. We know it exists because we can see its gravity affecting visible matter. Galaxies spin in ways that only make sense if there is much more matter present than we can see. Dark matter fills space, though we still do not know exactly what it is made of. Scientists are working hard to solve this mystery. Even in the parts of space that seem most empty, there is still not true nothingness. Quantum physics tells us that empty space is actually buzzing with activity at the tiniest scales. Particles pop in and out of existence for incredibly brief moments. This sounds strange, but it is part of how the universe works at the smallest levels. Myth 4. The Great Wall of China is visible from space for many years. People have said that the Great Wall of China is the only human-made structure visible from space. This myth has been repeated in textbooks, on television, and in casual conversation. Many people believe it without question. This myth is false. The Great Wall of China is not visible from space with the naked eye, and it is certainly not the only human-made thing you can see from orbit. Astronauts who have been in space have confirmed this. When they look down at Earth from the International Space Station, which orbits about 400 kilometers up, they cannot see the Great Wall without using a camera with a zoom lens. The Great Wall is very long, stretching for thousands of kilometers across China. But it is also very narrow, only about 6 to 7 meters wide in most places. From 400 kilometers away, something that narrow is impossible to see with human eyes. From space, astronauts can see many human-made things, but they are not structures like walls. Instead, they see things that are big and have different colors than their surroundings. Cities show up well at night because of all their lights. During the day, astronauts can sometimes see large cities as gray or brown patches that look different from the green or brown of natural land. They can see major highways in desert areas where the dark road contrasts with the light sand. Large dams and bridges might be visible in the right conditions. Agricultural areas often show up as patterns of different colors, with fields of different crops making a patchwork design. Mining areas can be visible because the exposed rock and dirt look different from the surrounding land. This myth probably started because the Great Wall is very impressive and very long. People knew it stretched for thousands of kilometers, so they assumed it must be visible from space. The myth grew as people repeated it without checking if it was true. Some people might have confused being visible from space with being visible from the moon. There was a claim that the Great Wall could be seen from the moon, which is about 384,000 kilometers away. This is definitely not true. From the moon, you cannot even see continents clearly, let alone a narrow wall. If we are talking about the furthest distance from which human-made objects can be seen, it is not the Great Wall. The lights of large cities can be seen from much farther away than the wall. In fact, Spacecraft traveling to the moon could see Earth's city lights glowing on the night side of the planet. Myth 5. The moon has a dark side that never sees sunlight. Many people talk about the dark side of the moon and think this means one side of the moon is always in darkness. They imagine one half of the moon in eternal night, never touched by the sun's light. This myth is so common that it has appeared in songs, movies, and books. There is no permanently dark side of the moon. All parts of the moon get sunlight at different times. What the moon does have is a far side. This is the side of the moon that always faces away from Earth. We never see it from Earth because the moon rotates at the same speed that it orbits around Earth. It takes the moon about 27.3 days to rotate once and about 27.3 days to orbit Earth once. Because these times match, the same side of the moon always faces us. But just because we cannot see the far side from Earth does not mean it is always dark. The far side gets just as much sunlight as the near side. Think about it this way. When we see a full moon from Earth, the entire side facing us is lit by the sun. At that same time, the far side of the moon is in darkness because it is facing away from the sun. But 2 weeks later, when we see a new moon from Earth, the side facing us is dark. At that same time, the far side is fully lit by the sun. As the moon goes through its phases over about 29.5 days, all parts of the moon get sunlight. During the moon's day, which lasts about 2 weeks, the sunlight slowly moves across the surface. Then comes the moon's night, which also lasts about 2 weeks. Until space exploration began, nobody had ever seen the far side of the moon. No telescope on Earth could show it because the moon always keeps that side turned away. It was not until October 4th, 1959, that humans first saw the far side. A Soviet spacecraft called Luna 3 flew around the moon and took pictures. These pictures surprised scientists. The far side looks quite different from the near side. It has many more craters and far fewer of the dark, smooth areas called Maria that we see on the near side. The phrase dark side of the moon probably stuck because it sounds mysterious. In English, we sometimes use dark to mean hidden or unknown, not just lacking light. So dark side makes sense as a way to describe the hidden, unknown side of the moon. But scientifically, it is wrong to say that side is always dark. The correct term is the far side of the moon, and scientists use this term to avoid confusion. Myth 6. Astronauts explode if exposed to space without a suit in many science fiction movies. When someone is exposed to the vacuum of space without a spacesuit, they explode immediately. Their bodies swell up and burst, or their blood boils and they freeze instantly. These dramatic scenes have convinced many people that exposure to space means instant death in a violent, explosive way. While space is definitely deadly and you would not survive for long, you would not explode. The reality is different from what movies show. If you were suddenly exposed to the vacuum of space, several things would happen, but exploding is not one of them. First, the air in your lungs would rush out. This would happen in seconds. If you tried to hold your breath, you could damage your lungs because the air inside would expand and could rupture lung tissue. This is why scuba divers are taught never to hold their breath while ascending, even in water. Your body would swell somewhat because there is no air pressure pushing on you from outside. On Earth, the air presses on your body with about 14.7 pounds per square inch. In space, there is no air, so nothing pushes back against the pressure inside your body. You might swell up to perhaps twice your normal size, but your skin is strong and elastic enough to hold you together. You would not burst. Contrary to what movies show, you would not freeze instantly. Space is very cold, but it is also a vacuum. Heat can leave your body in 3 ways: conduction, convection, and radiation. Conduction and convection both need matter to transfer heat. In a vacuum, there is no matter, so heat can only leave your body through radiation. Radiation is a slow way to lose heat. Your body would eventually cool down, but it would take a long time. You would not turn into a frozen solid in seconds. The real danger is the lack of oxygen. Your brain needs oxygen to work. After about 15 seconds without oxygen, you would pass out. After about 1 or 2 minutes, you would die from lack of oxygen. Decompression sickness would also be a problem. This is the same bends that scuba divers can get if they come up too fast. Nitrogen gas dissolved in your blood would form bubbles. This is painful and dangerous, but it would not cause you to explode. Your blood would not boil. Your circulatory system is a closed system with pressure from your heart. As long as your heart keeps beating, your blood stays liquid. The moisture on your tongue and eyes would evaporate because of the low pressure. This would be uncomfortable, but not immediately deadly. Scientists estimate that a human could survive in the vacuum of space for about 1 to 2 minutes before dying. Several seconds of exposure might not even cause permanent damage if you were brought back into a pressurized environment quickly enough and given oxygen. There have even been accidents where people were exposed to near vacuum conditions briefly and survived. In 1965, a technician at NASA had his suit rapidly depressurize in a vacuum chamber. He was conscious for about 14 seconds and then passed out. The chamber was repressurized quickly, and he recovered with no permanent injury. He reported that he could feel the saliva on his tongue starting to boil before he lost consciousness. Movies show explosive decompression because it is more dramatic and exciting than the reality. Watching someone slowly pass out is not as thrilling as seeing them explode. But the real science, while less dramatic, is the truth about what would happen in space. Myth 7. The sun is yellow. If you ask most people what color the sun is, they will say yellow. Children draw the sun as a yellow circle. We describe sunny days as having yellow sunshine. This seems obvious because when we look toward the sun, we see yellow light. The sun is actually white. It gives off light of all colors mixed together. And when you mix all the colors of light together, you get white. The sun looks yellow to us on Earth because of our atmosphere. When sunlight enters the atmosphere, it interacts with air molecules. This interaction affects different colors of light in different ways. Blue light has a shorter wavelength than red or yellow light. The atmosphere scatters blue light much more than it scatters red or yellow light. This is why the sky is blue. The blue light from the sun gets scattered in all directions by the atmosphere, making the whole sky look blue. When we look directly at the sun, we see the light that comes straight to us without being scattered. Because the blue light has been scattered away in all directions, more of the yellow and red light reaches our eyes directly. This makes the sun appear yellow or even orange, especially at sunrise and sunset, when the light has to travel through more atmosphere. If you could see the sun from space, where there is no atmosphere to scatter the light, it would look white. Astronauts who have seen the sun from space report that it is brilliant white, not yellow. Photographs taken from space also show the sun as white. When you see a picture of the sun that looks yellow or orange, it is either taken from Earth or the colors have been adjusted for artistic reasons, or to show specific features. The sun produces light across the entire visible spectrum and beyond. It makes red light, orange light, yellow light, green light, blue light, and violet light, plus ultraviolet light that we cannot see, and infrared light that we cannot see. All these colors together make white light. You can see this yourself with a prism. If you shine white light through a prism, it splits into all the colors of the rainbow. This shows that white light is really all colors combined. The same thing happens when you see a rainbow. Water droplets in the air act like tiny prisms, splitting sunlight into its different colors. Understanding the sun's true color helps us understand how light works and how our atmosphere affects what we see. It also reminds us that our perception of color can be influenced by many factors. What we see is not always the complete truth. Scientists who study the sun have to account for atmospheric effects when they make observations from Earth. This is one reason why space telescopes are so valuable. They can observe the sun and other objects without the atmosphere getting in the way. Myth 8. Black holes are cosmic vacuum cleaners. Many people think of black holes as giant vacuum cleaners in space, sucking up everything around them. They imagine that if a black hole formed anywhere near our solar system, it would pull in all the planets and the sun and destroy everything. Black holes do not suck things in like vacuum cleaners. They have gravity just like any other object, and this gravity only pulls on objects that come very close. Gravity works the same way for a black hole as it does for a star or planet. The strength of gravity depends on two things: how much mass an object has, and how far away you are from it. If the sun suddenly turned into a black hole with the same mass, Earth would keep orbiting just like it does now. The black hole would have the same gravity as the sun because it would have the same mass. Earth would not get pulled in. The only difference would be that Earth would get very cold and dark because the black hole would not produce heat and light like the sun does. What makes black holes special is not stronger gravity, but the fact that they are incredibly dense. All their mass is squeezed into a very tiny space. This creates an area around the black hole called the event horizon. If something crosses the event horizon, it can never escape because the escape velocity is faster than the speed of light, and nothing can travel faster than light. But the event horizon is usually quite small. For a black hole with the mass of our sun, the event horizon would be only about 3 kilometers across. You would have to get very close to be pulled in. Just like planets can orbit a star, objects can orbit a black hole. As long as they do not get too close, they will keep orbiting safely. In fact, scientists have observed stars orbiting close to the supermassive black hole at the center of our galaxy. These stars are not being sucked in. They are following stable orbits, going round and around the black hole for thousands of years. Black holes do pull in matter, but only when that matter gets close enough. Often, material falling toward a black hole forms a disk around it called an accretion disk. The matter in this disk spirals slowly inward over time. As it gets closer to the black hole, it speeds up and heats up, sometimes becoming so hot it glows with extra. This process can take a very long time. The material does not just get instantly vacuumed up. It spirals around many times before eventually crossing the event horizon. Black holes are also not nearly as common as some people fear. The nearest known black hole to Earth is about 1,000 light-years away. That is far enough that it has no effect on us whatsoever. At that distance, its gravity is incredibly weak. For a black hole to be dangerous to Earth, it would have to be extremely close within our solar system. This is incredibly unlikely to happen. Black holes do not move around hunting for planets to eat. They stay in orbit around the center of the galaxy, just like stars do. The black holes formed when giant stars die are only a few times more massive than our Sun. Even supermassive black holes at the centers of galaxies, which can be millions or billions times more massive than the Sun, only affect things that come very close to them. The rest of the galaxy orbits safely around them. Myth 9. Mercury is the hottest planet because it is closest to the Sun. It seems logical that Mercury, being the closest planet to the Sun, would be the hottest planet in our solar system. Many people assume this must be true. Venus is actually the hottest planet, even though it is farther from the Sun than Mercury is. Mercury is definitely hot. During the day on Mercury, temperatures can reach about 430 degrees Celsius. That is 430 degrees. This is hot enough to melt lead. But at night, temperatures on Mercury drop to about negative 180 degrees Celsius. That is a huge temperature difference between day and night. Mercury's day is very long. The planet rotates so slowly that one day on Mercury lasts about 59 Earth days. This means each side of the planet faces the Sun for a very long time and then faces away from the Sun for a very long time. Venus, on the other hand, has a surface temperature of about 470 degrees Celsius. That is 470 degrees. More importantly, this temperature is the same day and night at the equator and at the poles. Venus is consistently hotter than Mercury ever gets. The reason Venus is so hot is because of its atmosphere. Venus has a very thick atmosphere made mostly of carbon dioxide, with clouds of sulfuric acid. The atmosphere is so thick that the pressure at the surface is about 92 times the pressure at Earth's surface. This thick atmosphere creates a powerful greenhouse effect. When sunlight passes through the atmosphere and hits the surface of Venus, the surface heats up and gives off infrared radiation. But this infrared radiation cannot easily escape back into space because the thick atmosphere traps it. The heat builds up and builds up, making Venus incredibly hot. The greenhouse effect keeps Venus hot all the time, even at night, even at the poles. The temperature stays about the same because the atmosphere holds in all that heat. Mercury has almost no atmosphere. It does have a very thin layer of gases, but it is so thin that scientists call it an exosphere rather than a real atmosphere. An exosphere cannot hold in heat. So when the sun shines on Mercury, the surface gets very hot. But when the sun sets, all that heat quickly radiates away into space, and the temperature drops dramatically. This teaches us that being close to a heat source is not the only thing that determines temperature. The greenhouse effect, which depends on having the right kind of atmosphere, can make a huge difference. This is important for understanding Earth's climate too. Earth has a mild greenhouse effect that keeps our planet warm enough for life. But if our greenhouse effect gets too strong, like on Venus, it could make Earth much hotter. Venus shows us an extreme example of what can happen when greenhouse gases build up in an atmosphere. It is a reminder that atmospheres are important for determining a planet's temperature, sometimes even more important than distance from the sun. Myth 10. Shooting stars are actually stars. When people see a bright streak across the night sky, they often call it a shooting star or a falling star. This makes it sound like an actual star is moving across the sky or falling down from space. Shooting stars are not stars at all. They are small pieces of rock or dust from space, burning up in Earth's atmosphere. The scientific name for them is meteors. As Earth moves through space in its orbit around the Sun, it constantly runs into tiny bits of dust and rock. These pieces can be as small as a grain of sand or as large as a pebble. Most are very tiny. When one of these pieces enters Earth's atmosphere, it is moving very fast, often at speeds of about 50 to 70 kilometers per second. That is 50,0002, 70,000 meters per second. At these high speeds, the piece of rock or dust compresses the air in front of it. This compression heats the air to very high temperatures. The heat is so intense that the rock or dust starts to burn up. As it burns, it creates a bright streak of light across the sky. This is what we see as a shooting star. The whole event usually lasts only a second or two. Most meteors burn up completely before they reach the ground. The pieces are so small that they disintegrate entirely in the upper atmosphere. All that is left is a tiny amount of dust that slowly falls to Earth. Very rarely, a larger piece makes it through the atmosphere without burning up completely. If a piece lands on the ground, we call it a meteorite. Finding a meteorite is special because it is an actual piece of space rock that you can hold in your hand. Sometimes Earth passes through a stream of debris left behind by a comet. When this happens, we see many meteors in a short period of time. We call this a meteor shower. During a good meteor shower, you might see dozens of meteors per hour, all appearing to come from the same area of the sky. Each meteor shower happens at the same time every year, because Earth crosses that particular debris stream at the same point in its orbit. For example, the Perseid meteor shower happens every August, and the Geminid meteor shower happens every December. Real stars are enormous balls of burning gas very far away. They are so far away that they appear as tiny points of light. Stars do not move across the sky in streaks, and they certainly do not fall down. They stay in their positions relative to each other, though they do appear to move slowly across the sky during the night as Earth rotates. If a real star were to move, we probably would not see the motion because stars are so far away. Even stars that are moving very fast through space appear to stay in the same place from our viewpoint on Earth, because they are trillions of kilometers away. The name shooting star comes from a time before people understood what meteors really were. To observers long ago, it looked like a star was shooting across the sky. The name stuck, even though we now know better. It is a harmless name as long as people understand that shooting stars are not actually stars. They are visitors from space, little rocks and dust particles that put on a brief light show before disappearing forever. Myth 11. You can balance an egg on its end during the spring equinox. A persistent myth claims that you can balance a raw egg on its end during the spring equinox because of special gravitational conditions on that day. People hold egg balancing events on this day, convinced that it only works at this special time of year. You can balance an egg on its end any day of the year. There is nothing special about the equinox that makes it easier. The spring equinox is a day in March, when day and night are about equal in length everywhere on Earth. This happens because Earth's axis is tilted at about 23.5 degrees compared to its orbit around the Sun on the equinox. The Sun is directly above Earth's equator. The equinox is an important astronomical event, but it does not change gravity or make eggs easier to balance. Balancing an egg on its end is possible, but it is tricky. You need a patient hand, a good egg, and a surface with a little texture. The shell of an egg is not perfectly smooth. It has tiny bumps and variations. If you find the right spot where 3 or more of these tiny bumps can form a stable base, the egg will balance. Some eggs are easier to balance than others because of the shape of their shells and the distribution of weight inside. It might take several tries, but with patience, you can balance an egg any day of the year. This myth seems to have started in the 1940s when a magazine article mentioned egg balancing during the equinox. The idea caught on and spread. People started holding egg balancing events on the equinox, and when eggs balanced successfully, they took it as proof that the myth was true. But eggs balanced because people were being careful and patient, not because of the date. If those same people tried to balance eggs on other days with the same care, they would succeed then too. Some people think that the alignment of Earth and the Sun during the equinox somehow changes gravity. This is not true. The Sun does have gravity that affects Earth, but this gravity does not change in any noticeable way during the equinox. The change in the position of the Sun relative to Earth's equator does not affect gravity enough to influence something as small as an egg. The gravitational forces from the Sun and Moon do cause tides in Earth's oceans, but these forces are spread out over huge distances and massive amounts of water. They cannot make an egg easier to balance on a kitchen counter. Scientists and curious people have tested this myth many times. They have successfully balanced eggs on days that are not the equinox, proving that there is nothing special about that day for egg balancing. If you want to try balancing an egg, go ahead and try it today. Whatever day it is. You might need several attempts, but it is possible. Just do not wait for the equinox, thinking it will be easier then. Myth 12. The North Star is the brightest star in the sky. Many people believe that the North Star, also called Polaris, is the brightest star in the night sky. They think this must be true because the North Star is so important for navigation. The North Star is not even close to being the brightest star in the sky. It is only the 48th brightest star, and many stars are much brighter than it is. The actual brightest star in the night sky is Sirius, also called the Dog Star. Sirius is more than 20 times brighter than the North Star. You can see Sirius from anywhere in the southern 2/3 of Earth. In the winter months, In the northern hemisphere, it is very noticeable low in the southern sky. Other very bright stars include Canopus, Arcturus, Rigel, and Vega. All of these are much brighter than the North Star. The North Star is important, not because it is bright, but because of its location. It sits almost directly above Earth's North Pole. This means that as Earth rotates, the North Star stays in almost the same spot in the sky, while all the other stars appear to move in circles around it. If you are in the northern hemisphere and you can find the North Star, you know which direction is north. This has been extremely useful for navigation throughout human history. Sailors and travelers used the North Star to find their way, especially before compasses and GPS existed. The North Star is not hard to find if you know how to look for it. First, find the Big Dipper, which is a group of 7 bright stars that form a shape like a pot with a handle. Then look at the 2 stars that form the outer edge of the pot, away from the handle. If you draw an imaginary line through these 2 stars and extend it away from the pot, the line will point to the North Star. The North Star is bright enough to see easily once you know where to look, but it is not remarkably bright compared to other stars in the sky. Earth's axis wobbles slightly over a very long period, about 26,000 years. This means that the North Star changes over time. Right now, Polaris is the North Star, but thousands of years ago, other stars were closer to the North Celestial Pole. Thousands of years from now, different stars will take the title. About 5,000 years ago, when the ancient Egyptians were building the pyramids, a star called Thuban was the North Star. About 12,000 years from now, a bright star called Vega will become the North Star. People probably assume the North Star is the brightest because it is famous and important. Throughout history, it has been mentioned in stories, songs, and teachings about navigation. This fame makes people think it must be special in other ways too, like being the brightest. But brightness and importance are not the same thing. Myth 13. Astronauts are weightless in space. This myth is related to the myth about gravity in space, but it is worth addressing separately. Many people say that astronauts in space are weightless or have zero gravity. Astronauts are not truly weightless. Weight is the force of gravity pulling on an object. As we discussed earlier, gravity exists everywhere in space. The International Space Station is only about 400 kilometers above Earth, and gravity there is about 90% as strong as on the ground. What astronauts actually experience is called microgravity or free fall. They are falling toward Earth all the time, but because the space station is also moving forward very fast. They keep missing the Earth and orbiting around it instead. Because the astronauts and the space station are falling together at the same rate, it feels like floating. If the astronauts let go of an object, it floats beside them because it is also falling at the same rate. Everything inside the station is in free fall together. Scientists prefer to use the term microgravity rather than zero gravity. Micro means tiny, and there are tiny variations in the gravitational force across the space station. Also, the space station itself has a little bit of gravity because it has mass, though this is incredibly small. Other forces also affect objects in the space station, like air resistance from the thin traces of atmosphere at that altitude and pressure from sunlight. These forces are very small but not zero. Understanding the difference between true weightlessness and free fall matters for science. It affects how experiments are designed and how astronauts train. It also helps people understand how orbits work. If there were truly no gravity in space, satellites would not stay in orbit. They would fly off in straight lines. Orbits only work because gravity is constantly pulling satellites toward Earth, while their sideways motion carries them forward. You do not have to go to space to experience what astronauts feel. Special airplanes can fly in a curved path that creates brief periods of free fall. These planes climb steeply, then curve over and dive down. During the curved part of the flight, passengers inside float around just like astronauts do. Each period of floating only lasts about 25 seconds before the plane has to pull up and climb again. But during that time, you feel exactly what astronauts feel in the space station. You also experience a tiny bit of free fall when you jump. For the brief moment that you are in the air with no contact with the ground, you are in free fall. You fall so quickly that you barely notice the feeling, but it is the same physics. Myth 14. There is a face on Mars in 1976. A spacecraft called Viking 1 took a picture of the surface of Mars. In the picture, a mesa or hill seemed to look like a human face. Some people became convinced that this was evidence of alien civilization on Mars. They thought aliens had carved a giant face into the Martian surface. The face on Mars is just a mesa, a natural hill. It only looked like a face because of the angle of the sunlight and the low resolution of the early photographs. The original photo from Viking 1 showed a hill in a region called Cydonia. The lighting conditions and shadows at that moment made the hill appear to have two eyes, a nose, and a mouth. It was a classic case of pareidolia, which is when our brains see familiar patterns, especially faces in random shapes. Humans are very good at seeing faces. Our brains are wired to recognize faces because this was important for survival. This means we often see faces in clouds, in tree bark, in the pattern of tiles on a floor, and even on hills on Mars. As technology improved and more spacecraft visited Mars, they took better photographs of the same area. The Mars Global Surveyor spacecraft took high-resolution images of the Mesa in 1998 and again in 2001. These images were taken from different angles and in different lighting conditions. The better photographs show that the Mesa is just a natural rock formation. It does not look like a face at all in the new images. The original face appearance was purely due to shadows and low image quality. The Mars Reconnaissance Orbiter, which has even better cameras, also photographed the area. Its images show even more clearly that this is just an ordinary mesa. Similar to mesas found on Earth, people have found other supposed faces and structures on Mars and even on the Moon, always in low resolution or ambiguous images. Each time better photographs are taken, these features turn out to be natural rock formations that only looked unusual because of lighting or image quality. This is a good reminder to be skeptical of claims based on poor quality evidence. When you see a strange pattern in a blurry image, the most likely explanation is that it is a natural formation, and your brain is finding patterns that are not really there. Despite the clear evidence from better photographs, some people still believe in the face on Mars. They think that NASA is hiding evidence of aliens, or that the better photographs have been altered. This shows how powerful myths can be, even when contradicted by evidence. The face on Mars has become a popular culture phenomenon, appearing in movies, television shows, and books. This keeps the myth alive, even though science has thoroughly debunked it. Myth 15. Meteors are hot when they land in movies and cartoons. When a meteor lands, it is shown glowing red hot, sometimes setting fires or melting into the ground. This gives people the impression that meteorites are extremely hot when they hit the ground. Most meteorites are actually cold or only slightly warm when they land. Some are even covered in frost. When a meteoroid enters Earth's atmosphere, it is moving very fast, and the compression of air in front of it creates intense heat. This heat melts the outer surface of the meteoroid, creating a thin coating called a fusion crust. However, this heating only affects the outer surface. The inside of the meteoroid stays cold because stone and metal do not conduct heat very well, and the heating phase is very brief, usually lasting only a few seconds. After the meteoroid has slowed down enough that it stops burning, it still has to fall the rest of the way to the ground. This can take several minutes. During this time, the meteorite is passing through the cold upper atmosphere. The heat from the fusion crust is lost to the surrounding air. By the time the meteorite lands, it is often cool to the touch. Some witnesses have reported picking up meteorites within minutes of seeing them fall and finding them only slightly warm or even cold. In some cases, meteorites have been found with frost on them from passing through the cold upper atmosphere. The fusion crust on a meteorite is very thin, usually only a few millimeters thick. It is black or dark brown and looks smooth or slightly rough. This crust forms during the few seconds of intense heating and then quickly cools. It is evidence that the meteorite did experience high temperatures, but it does not mean the whole meteorite stayed hot. Movies show meteorites glowing hot because it is more dramatic and helps viewers understand that something just came from space. A glowing, smoking rock is more exciting than a cold, dark one. But dramatic is not the same as accurate. Very large meteorites that make it through the atmosphere can stay warm or even hot inside because their larger mass holds heat better. But even these cool down relatively quickly. Unless you are right at the impact site within seconds of the landing, you are unlikely to encounter a hot meteorite. Also, most meteorites that people find were not seen falling. They are old meteorites that have been sitting on the ground for months, years, or even thousands of years. These are definitely not hot. Myth 16. All stars twinkle. When we look at the night sky, we see stars twinkling. They seem to shimmer and flash with different colors. This has led many people to believe that all stars naturally twinkle. Stars do not actually twinkle. The twinkling happens because of Earth's atmosphere. If you could see stars from space, they would shine with steady light. Light from stars has to travel through Earth's atmosphere before it reaches our eyes. The atmosphere is not perfectly still. It is constantly moving and swirling. Different layers of air have different temperatures and densities. As starlight passes through these moving layers of air, its path bends slightly. This bending changes from moment to moment as the air moves. Sometimes the light is bent toward your eye, making the star appear brighter. A moment later, the light might be bent slightly away, making the star appear dimmer. These rapid changes in brightness are what we see as twinkling. The technical term for twinkling is scintillation. It is the same effect that makes objects appear to shimmer when you look at them across a hot parking lot on a summer day. The heat makes the air move and creates different densities, which bend light in changing ways. Planets in our solar system do not usually twinkle as much as stars do. This is because planets are close enough to Earth that they appear as tiny disks rather than points of light. Even though you need a telescope to see them as disks, they are still disks to your eye rather than pure points. Because a planet's light comes from a small disk rather than a single point. The atmospheric effects that make one part of the disk brighter balance out the effects that make another part dimmer. The result is steadier light. This is actually one way to tell planets from stars. If you see a bright object in the sky that is not twinkling much, it might be a planet. If it is twinkling a lot, it is probably a star. Astronauts looking at stars from the International Space Station or from the moon do not see them twinkle. The stars shine with constant, steady light. Without an atmosphere to look through, there is no twinkling. This is one reason why astronomers like to use space telescopes. Without atmospheric distortion, they can take much clearer pictures of stars and other objects in space. Not all stars twinkle the same amount. Stars that are lower in the sky twinkle more than stars that are high overhead. This is because light from stars near the horizon has to pass through more atmosphere to reach your eyes. More atmosphere means more turbulence and more twinkling. On some nights, the atmosphere is calmer and stars twinkle less. On other nights, when there is a lot of turbulence in the atmosphere, stars twinkle more. Astronomers prefer calm nights for making observations because the stars are steadier. Even though twinkling is caused by our atmosphere and not by the stars themselves, it is still beautiful. The shimmering of stars has inspired countless poems, songs, and works of art throughout human history. Understanding the science behind twinkling does not make it any less wonderful to watch. Myth 17. Seasons are caused by distance from the sun many. People think that summer happens when Earth is closest to the sun, and winter happens when Earth is farthest from the sun. This seems logical because we associate heat with being close to something hot. Seasons are caused by the tilt of Earth's axis, not by changing distance from the sun. Earth's axis is tilted about 23.5 degrees compared to its orbit around the sun. This means that as Earth goes around the sun during the year, different parts of Earth are tilted toward or away from the sun at different times. When the northern hemisphere is tilted toward the sun, it is summer there. The sun's rays hit that part of Earth more directly, and the days are longer. At the same time, the southern hemisphere is tilted away from the sun, so it is winter there. The sun's rays hit at a shallower angle, and the days are shorter. 6 months later, Earth has moved to the opposite side of its orbit. Now the northern hemisphere is tilted away from the sun, and it is winter there. The southern hemisphere is tilted toward the sun, and it is summer there. Earth's orbit is not a perfect circle. It is slightly elliptical, which means Earth is sometimes closer to the sun and sometimes farther away. But this difference is small, only about 5 million kilometers out of an average distance of about 150 million kilometers. That is a change of only about 3%. More importantly, Earth is actually closest to the sun in early January, during winter in the northern hemisphere. Earth is farthest from the sun in early July, during summer in the northern hemisphere. This proves that distance is not what causes the seasons. The tilt of Earth's axis has a much bigger effect on temperature than the small change in distance does. When sunlight hits Earth more directly, it is more concentrated and provides more heat. When sunlight hits at a shallow angle, it is spread out over a larger area and provides less heat. Also, when a hemisphere is tilted toward the sun stays above the horizon for more hours each day. This means more time for the sun to heat the ground. Longer days and more direct sunlight combine to create summer. When a hemisphere is tilted away from the sun, days are shorter and sunlight is less direct. This creates winter. At the equator, there is very little change in seasons. The sun is always fairly high in the sky, and day and night are about equal in length all year round. This is because the equator is not strongly affected by Earth's tilt. It is always pointing roughly toward the sun. The farther you go from the equator, the more extreme the seasons become. Near the poles, summer has very long days, or even 24-hour daylight. Winter has very short days, or even 24-hour darkness, because Earth's tilt causes opposite seasons in the northern and southern hemispheres. People on different parts of Earth experience very different weather at the same time. While people in North America are building snowmen in December, people in Australia are going to the beach. This would not happen if seasons were caused by distance from the sun. If distance were the cause, the whole planet would be warm or cold at the same time. Myth 18. You can see the Great Wall of China from the moon. An extension of the myth about seeing the Great Wall from space is the claim that you can see it from the moon. This takes the myth to an even more extreme level. You absolutely cannot see the Great Wall of China from the moon, and you cannot see any human-made structures from there either. The moon is about 384,000 kilometers from Earth. From that distance, Earth looks like a small disk, about the size of a coin held at arm's length. When you look at Earth from the moon, you can see continents and oceans. You can see clouds and ice caps, but you cannot see individual structures, roads, or buildings. Everything is too small. 12 astronauts have walked on the moon during the Apollo missions. They all looked back at Earth, and none of them could see any human-made structures. They saw Earth as a beautiful blue marble with white clouds, brown and green land masses, and white ice caps. But no Great Wall, no cities, no roads. The photographs taken from the moon show the same thing. Earth is beautiful, but lacks visible detail. You cannot pick out any human construction. Let's think about the size of the Great Wall compared to the distance to the moon. The Great Wall is about 6 to 7 meters wide on average. The moon is 384,000 kilometers away. That is 384 million meters. From that distance, trying to see a 7-meter wide wall would be like trying to see a human hair from 2 kilometers away. It is simply not possible with the naked eye. Even with a telescope, you could not see the Great Wall from the moon. You would need an impossibly large telescope with a lens or mirror many kilometers across. No such telescope exists or could practically be built. The best telescopes on Earth can take pictures of details on the moon that are only about 1 meter across. But the moon is much closer to Earth than Earth is to the moon, and even these powerful telescopes cannot see everything. The one thing that is visible from the moon with help is light. When Apollo astronauts were coming back from the moon and were at a distance where Earth was still relatively small in their window, they could see the lights of cities on the night side of Earth. But even this required dark adaptation of their eyes and very good viewing conditions. It was not easy or obvious. These lights are visible not because of individual streetlights, but because of the combined glow of millions of lights in a city altogether. And this is still not the same as seeing structures or buildings. It is just seeing patches of light. The idea that you can see the Great Wall from the moon is completely false. It is an exaggeration of the already false claim about seeing it from low Earth orbit. Understanding how far away the moon is and how small the Great Wall is helps us realize why this myth cannot be true. Myth 19. Space is always dark. When people think of space, They often imagine total darkness everywhere, except for the occasional star or planet. They think that if you went to space, it would be like being in a dark room. Space itself does not have light or darkness. Light is something that travels through space. Whether a place in space seems bright or dark depends on whether there is a source of light nearby and what direction you are looking. If you were in a spacecraft in our solar system, space would not seem particularly dark, at least not in all directions. If you looked toward the sun, it would be intensely bright, much brighter than it appears from Earth's surface, because there is no atmosphere to dim it. If you looked away from the sun, you would see stars, but they would not light up the space around you very much, because they are so far away. So in that direction, space would seem dark. The surface of the moon, which has no atmosphere, is very bright when the sun is shining on it. Photographs from the Apollo missions show astronauts and equipment brightly lit by sunlight, even though there is no atmosphere to scatter the light and create a blue sky. From the moon or from a spacecraft, the sky is black even during the day. This is because there is no atmosphere to scatter sunlight. On Earth, our sky is blue during the day because air molecules scatter blue light in all directions. In space, there is no air to scatter light, so the sky is always black. But black sky does not mean darkness. If the sun is up, there is plenty of light shining directly from the sun. Objects in sunlight are brightly lit. Objects in shadow are dark because there is no scattered light to illuminate them. But that is different from saying space itself is always dark. In the regions between stars, far from any sun, space is indeed very dark. There is no nearby light source to illuminate anything. The only light is the faint glow of distant stars and galaxies. But even there, space is not completely dark. There is the cosmic microwave background radiation left over from the Big Bang. This radiation is very faint, and in wavelengths we cannot see with our eyes, but it is there, filling all of space. Whether space seems bright or dark depends on where you are and what is nearby. Near a star, there is bright light. In the shadow of a planet or moon, it is dark. In the space between galaxies, it is very dark. There is no single answer to whether space is bright or dark. Astronauts on the International Space Station see sunrise and sunset every 90 minutes as they orbit Earth. When the sun is visible, the space around them is filled with bright light. When Earth blocks the sun, they are in shadow and it is dark. Their experience is not of constant darkness, but of alternating light and dark. Myth 20. A year in space is much different from an Earth year. Some people think that spending a year in space means experiencing a very different amount of time than a year on Earth. They might confuse this with the science fiction concept of time dilation. A year in space is the same as a year on Earth for practical purposes. Time passes at the same rate. It is true that according to Einstein's theory of relativity, time passes slightly differently depending on speed and gravity. Astronauts on the International Space Station are moving very fast in orbit, and they are in slightly weaker gravity than on Earth's surface. These factors do cause time to pass very slightly differently for them, but the effect is extremely tiny. After spending 6 months on the International Space Station, an astronaut will have aged about 0.007 seconds less than people on Earth. That is about 7 milliseconds, less than 1/100th of a second. This difference is so small that you would never notice it. You cannot see it, feel it, or measure it without extremely precise atomic clocks. For all practical purposes, time passes the same on the space station as it does on Earth. When astronauts come back to Earth after a long mission, they have not time traveled. They are the same age they would be if they had stayed on Earth, give or take a few thousandths of a second. Time dilation only becomes noticeable when speeds get close to the speed of light, or when gravity becomes very strong, like near a black hole. The fastest human-made spacecraft are still moving at tiny fractions of the speed of light. Light travels at about 300,000 kilometers per second. The Parker Solar Probe, one of the fastest spacecraft ever built, reaches speeds of about 190 kilometers per second at its fastest. That is very fast, but it is still only about 0.06% of the speed of light. At that speed, time dilation is still extremely small. To experience time dilation that you could actually notice, you would need to travel at a large fraction of the speed of light, which is far beyond our current technology. Or you would need to be very close to a black hole, which would be very dangerous for other reasons. One place where time dilation does matter is in GPS satellites. These satellites orbit Earth at high speeds and in weaker gravity. The combination of these effects means that time passes very slightly differently for the satellites than for people on the ground. This tiny difference is enough to matter for GPS, because GPS works by measuring the time it takes signals to travel from satellites to your phone or GPS device. If the satellite clocks were not adjusted for time dilation effects, GPS would become inaccurate very quickly, gaining errors of several kilometers per day. So scientists adjust the satellite clocks to account for relativity. This is one of the few everyday technologies where Einstein's theories of relativity are actually important. When astronauts talk about spending a year in space, they mean a year as measured by Earth time. They eat 3 meals a day, sleep 8 hours a night, and experience 365 days just like people on Earth. Their experience of time is the same as ours. Space is full of wonders and mysteries, but we do not need to believe false information to find it fascinating. The real facts about space are amazing enough on their own. Many myths about space come from outdated science, misunderstandings, or science fiction movies that take dramatic license with the truth. By understanding the real science, we can better appreciate how incredible the universe actually is. Gravity exists everywhere, working constantly to hold the universe together. Stars produce light through nuclear fusion, not fire. Black holes are not vacuum cleaners, but dense objects with powerful gravity near them. The sun is white, not yellow. Meteors are small rocks burning up, not falling stars. And astronauts float because they are in free fall, not because there is no gravity. Learning the truth about these myths helps us think more clearly about space and science in general. It teaches us to question what we hear and to look for evidence before accepting claims. It shows us that science is about discovering how the world really works, even when the truth is different from what we assumed. The universe is vast, ancient, and full of things we are still learning about. Dark matter, dark energy, the possibility of life on other worlds, the nature of black holes, the origin and fate of the universe. These are real mysteries that scientists are working to solve. We do not need to make up mysteries when so many real ones exist. As we continue to explore space with better telescopes, more advanced spacecraft, and new scientific instruments, we will learn even more about our universe. Some of what we know now might turn out to be wrong, and new discoveries will replace old ideas. That is how science works. It is always updating itself as we gather new evidence. But the process of discovering the truth is important. We cannot make progress if we hold onto myths instead of facts. By debunking these common myths, we make room for real understanding. Whether you are looking up at the stars at night, reading about new discoveries, or just curious about how things work, remember to ask questions and look for evidence. Science is for everyone, and the true nature of space is more wonderful than any myth. The next time someone tells you that the Great Wall of China is visible from the moon, or that the sun is on fire, or that there is no gravity in space, you will know better. You will know the facts, and perhaps you can help them understand the truth too. Space exploration and astronomy are some of humanity's greatest achievements. From ancient people who first noticed patterns in the stars to modern scientists operating space telescopes and sending rovers to Mars, humans have always wanted to understand the universe. By learning the real facts and letting go of myths, we honor that tradition of curiosity and discovery. We become part of the ongoing human effort to understand our place in the cosmos. So look up at the night sky with wonder, but also with knowledge. The stars you see are not twinkling on their own. Earth's atmosphere makes them shimmer. The shooting stars are not stars at all, but small pieces of rock burning up. The North Star you use to find direction is not the brightest star, but it is in the perfect position to guide you. Every fact you learn about space adds to your understanding of the universe and your place in it. And in this vast, ancient, beautiful universe, that understanding is one of the most valuable things we can have. The myths about space will probably never go away completely. They are too widespread and too deeply embedded in our culture. But the more people who know the truth, the less power these myths have. Knowledge spreads, just like myths do, but knowledge has the advantage of being true. As you go forward, share what you have learned. When you hear someone repeating one of these myths, politely correct them. Explain the real science in simple terms. Help others discover the same fascinating facts that you now know. The universe is waiting to be understood. Every myth we debunk brings us one step closer to that understanding, and every person who learns the truth becomes part of humanity's collective journey to know the cosmos. Thank you for taking this journey through space myths with me. I hope you have learned something new and that you will continue to explore the real science of our amazing universe. The truth is out there, and it is more wonderful than any myth could ever be.